Hello, I'm Alberto Solera. I'm a first-year student under the supervision of Stefano Isetti and Carlos San Miguel. And I also work at INTA, the Spanish National Institute for Aerospace Technology. And I will talk about my PhD thesis on the use of data-driven methods for active flow control. As a context, we know that transport represents about a quarter of the greenhouse emissions in Europe, and is one of the main pollutants in cities. In particular, aerodynamic drag is a significant portion of that losses and so emissions. And for transport trucks, it represents about 20% of the total losses. This has been traditionally tackled by basic geometric optimization, basic or complex. But for example, in this case, the extra space occupied by these aerodynamical flaps is not practically useful because this space is usually occupied by extra cargo and it has some economical benefits. So we want to explore an alternative solution using new possibilities in data-driven active flow control that offer the potential to efficiently build control systems that use less energy for the actuation than the savings achieved by the result, and do it in a constrained environment, in the sense that, for example, we don't change the external geometry of the vehicle, and under variable conditions, for example, at different velocities and so on. So, regarding active flow control, the machine learning can be applied in different areas. In particular, we will focus on building reduced order models that keep the essential information of the flow and also are useful to discard the noise, the high frequency noise, and reduce the dimensionality and the resulting computational cost of the methods. In order to use that reduced representation, we have to map the information we have from a few sensors placed in the vehicle to that low dimensional space to be able to then propagate the state, for example, using data-driven models. And lastly, we want to learn complex flow control algorithms that use that information received by the sensors, mapped to the low dimensional space to use as well as possible the actuators to reduce the drag or optimize any other cost function that we might have. This is a current trend in academia. There are many recent publications on the area, and it has expected application in industry in the near or midterm. We can see here an example of the controlling the wake of a cylinder with reinforcement learning. The main research question for my work are whether a reduced order representation still contains meaningful information for flow control algorithms. We usually optimize them to reconstruct as much energy as possible, but we want to test if this information is useful as feedback for a control algorithm. We want to validate that idea of mapping the sensors measurements to the same low-dimensional space obtained by the reduced order model. And we want to test if that reduced order models can be used as a predictor, as we were talking before, for a model predictive controller, or even as an environment for a reinforcement learning agent. Maybe not for the final training, but probably for pre-training the agent in a faster way. Machine learning can be applied in several areas of both model predictive controller and reinforcement learning. We can use it as environment, as I was saying, as an interpreter to map the sensor information to the controller space, and also to build the controller itself. The same, more or less, for model predictive control. For this first year, we have been focused on preparing some experimental setup at INTA facilities. We have a new wind tunnel, LDA and PhD equipment. And also, we have been building some simulated datasets in order to then train the models to come. We have also started work on deep learning for fluid dynamics. We have a work in progress on a super resolution algorithm for PhD measurements using a generative adversarial network. This is an extension of a previous work by the group to three dimensions. And we are also exploring some physical constraints to the solution. We have also worked in reduced order modeling using beta variation autoencoders and transformers for model decomposition and prediction of the system state. This is currently under review at Nature Communications. And the planning for the following years are to, first of all, build reduced order models with actuation input. We need it in order to use that control inputs from the control algorithm. We want to test the control using that reduced representation as feedback from the system state. We are exploring, we will be exploring model predictive control and reinforcement learning. And we want to do it in simulation, where we can explore the limited sensing or reduced order models environment. And also in real time, where experimental setups, where the real-time implementation is, as we were talking also, the main challenge. Let's see what is the resulting control frequency that we can achieve using these methods. These are some reference from the last year or even less that show that this is a very active area in academia. In particular, machine learning for flow control, using data-driven reduced order models for reinforcement learning, and some perspectives on flow control. And that's all. Thank you for your attention, and I am open to any question.